Thank you for joining us today for our Passive House Lunch and Learn. So I'm Aaron Gunnarsson. I'm just facilitating today. Steve Demetric is on your screen. He'll be today's featured presenter, and I'll introduce him in a moment. But I have a few slides to go through here and some announcements about our Mass Save Passive House and All Electric Homes training program. But once again, thank you for being here for today's Passive House Lunch and Learn, sponsored by the Mass Save training program here. So I think a lot of you are familiar with the Mass Save program at this point. For last several years now, they've been generously doing trainings and incentives for Passive House projects and Passive House professionals in the state. This is the newest incentive program and pretty and kind of the key one that we're highlighting today in today's Lunch and Learn All Electric Homes is their All Electric Home Incentive. So this is for 1 to 4 unit buildings, so single family buildings and larger ones up to 4 units. But some pretty excellent incentives here in order to encourage new homes to move towards electrification and all electric. So you can see on the right that this chart there is showing you level 1 and level 2. So there's sort of 2 different levels of incentives depending on how far you take your project in terms of steps to become all electric and in terms of energy performance. So these incentives don't require you to become a Passive House certified project, but they do require significant energy reduction. The first row on that chart highlights the energy savings that they're looking for, and the HERS scores that you can see. The level 2 HERS score of 35. That's around a Passive House level performance. Passive House will definitely get you there. So you can kind of keep thinking in that headspace about it. But pretty great incentives to get those level 2 incentives in a single family home. See $25,000. So nothing to joke about here. Some pretty good incentives. In addition to that, there's the ongoing ones for larger projects, not as relevant to today's session, but always good to remind folks that these exist for buildings that are 5 units or more. And I believe the last numbers I've heard were over 12,000 units enrolled in this incentive program, which is pretty exciting. This is going a long way to driving the demand for Passive House we're seeing here in Massachusetts. So really excellent incentives. But thank you for listening to me. I'm going to go ahead and turn things over to our featured presenter, Steve Demetric, who's going to take things away. Again, just a reminder for our audience, please keep yourself on mute throughout today's session. You can use the chat room to ask questions or make comments. And at the end of Steve's presentation, I'll open it up to questions. So I'll read some from the chat room. I'll also allow you guys to raise your hand, use the raise hand feature and ask them directly then. But for now, keep yourself on mute. All right, Steve, I'm going to stop sharing my screen. You can go ahead and share yours. Folks, Steve Demetric should be on your screen right now. Steve is a certified Passive House builder, built the first Passive House in Rhode Island, came up to Massachusetts a lot and used to be a board member for Passive House Massachusetts. Now he's one of the founders for Passive House Rhode Island, a group starting up down there. But he's involved in a wide variety of different types of residential projects. Today, he's going to talk about an all-electric Passive House case study. So Steve, go ahead and take it away.
Yeah. All right. Thanks, Aaron. Good afternoon, everybody. My first Zoom presentation, so it's a little awkward talking to a screen, knowing there's a bunch of people out there, but I'll try to make the best of it. Yeah, Aaron basically summarized what we do. I'm a small residential contractor. I've been focused completely on net zero and Passive House aligned buildings since I built the first one in Rhode Island in like 2015 or so. And that was 4 years after I did the certified Passive House builder training. And once I built the first one, I realized how simple it actually could be, and I haven't looked back. And so now we are mostly doing single family residential new construction. We do a little bit of remodeling, but our focus really is on building smaller Passive House aligned or Passive House certified residential buildings. And we also are focused on building smaller homes as well. Like we're really trying to provide opportunities for people that are looking for a first home or smaller retirement home versus the larger custom homes, which seem to be a lot of what are the projects that you see presented on are just larger homes that have a lot of features and details that make it difficult for people to extrapolate information details that would be relevant to the type of buildings that most people need. So this presentation is really focusing on a house that we built in Charlestown, Rhode Island the other year, and we're building a similar one next door and have 2 more coming up. So there's a couple of pictures of this house. So this is a single family. This is the house I'm going to be talking about today. I'm going to walk through our process and our the details. So this is a single family home. It's 3 bedrooms, 2.5 baths, kitchen, living room space. It's about 1,700 square feet inside, more or less. Just a couple of pictures of the outside. And a couple of things we're focusing on as a company besides net zero building is also we're focusing a lot on sustainability and specifically material choices in the buildings that we're creating. So if you can see on this house, like the exterior is 100% wood siding. And so when we add that to the wood framing, the cellulose insulation, and not this house, but the next house that we're building right now, we removed the foam under the slab and used Glavel. So when you start doing some carbon calculations, we're actually having an impact there as well. A couple interior shots, the kitchen, second floor. You can see we have a little mini split up in the corner. So before I get into the presentation, I just want to talk a little bit about the energy benefits of what we're doing and differentiate what we're doing versus a code-built house. And this is specific to Rhode Island. I know the building code in Rhode Island is not as advanced as it is in Massachusetts. But I've been working closely with someone from Clear Result, which manages the utility programs in Rhode Island. And he's been taking our homes and then modeling them. He's modeling them as part of the program, but then he's also taking the time to model them as if a code builder, spec house builder was building the same house. And you can see the radical difference in what a code built house in Rhode Island would look like versus our homes. We've got R10 under the slab, we go up to R20, which is continuous versus under code, it's only the first couple feet. We go from R21 in the walls, no thermal bridging considered, to dense packed cellulose. R38 in the ceiling goes to R90, 5 air changes per hour. That's reality in Rhode Island. A lot of people are failing. And we're at 0.3 air changes in this house. We go from 0.35 U value windows to 0.12. Gas furnace to a heat pump, gas hot water heater to heat pump water heaters, and then just much more energy efficient air conditioning. And then the big one too is ventilation, and that's a completely separate topic, but not to do with energy, but just for indoor air quality and health of the occupants. That balanced ventilation is definitely key, and not something you can put into the spreadsheet for value, but it's definitely the value that's there. And so these are some numbers that that we've come up with so far based on our modeling. So that's this house that you just saw in the first picture. If we were to build it to code with a spec house builder, this is our peak loads for that house. And as designed and built, the modeling came up with 9,600 kBTUs per hour, significant reduction there. And that's, yeah, massive savings there. And so that's our peak loads. And then annual consumption, we end up with the code built house, we're at 68 million BTUs per year. And as designed with our heat pumps, that works out to 5 million BTUs a year, that's a massive reduction with those change in specifications. And then monthly savings, we calculate $257, annual savings $3,000, and you can see the 30 years, the payback is real. And this particular house as well, this was built without solar panels, and they did put solar panels on after the first 6 months. And I don't have the utility bills from them yet, but from what they've said, they're actually at I think they're net positive right now with their solar panels. And the comparison here for you can see before as another summary of it was we're changing from natural gas boilers to heat pumps. You can see the benefit. These are all the benefits that come out of that. So now I'm going to get into the kind of our construction details. And this is an old slide. I first saw this probably, I don't know, 10 or 12 years ago. And actually not that long, maybe 8 years ago. But I've always gone back to it in our presentations because it really defines everything that we're talking about in these projects. And it captures the concept that we're trying to share with our customers through the design process, is simplifying these details and so that we can apply them more effectively on these homes. And I love the simplicity of this drawing. You can see the red here is just our air barrier. just that concept of keeping a really simple continuous air barrier. The other concept here, the blue, just here's our continuous insulation, thermally broken all the way through. Here's our balanced ventilation, another key component to these structures. So I got our exhaust air coming out, our fresh air coming in. Not quite drawn to code. I don't think we have the separation we need there, but that's okay. And then also detailing for overhangs. So you can see these long overhangs, how it affects the amount of solar gain in the project. And that's another variable that's not calculated very accurately in those heating loads I was sharing earlier, because most spec builders would have removed the overhangs on our house, because right now they're at 2 feet and they probably would be a foot or less or non-existent. So another variable to consider. So I just want to kind of walk through what our approach is, and how we're thinking of our projects as we're moving into them. So our recipe for this is really we're taking our knowledge and putting it to use, and we're also committing to high performance details. And I do feel that for people that are just starting out, that are trying to understand how to do these things and how to apply these things to a home, I think more important than learning the knowledge is committing to using it. Because as you commit to using it, the knowledge will come from practice. Basically, that's how it's worked for me. I started studying high performance building, gosh, probably 2007 or 8 when I did the BPI course, and ever since then, every little bit has been applying it and learning it. And the more you apply it, the more it sinks in, and the more you understand it, and the more effectively you can apply it then. The other thing that's been really important to us in our approach is to really simplify our construction details, mainly because a lot of the work being done on these homes is being done by subcontractors who are not Passive House certified. They don't really understand the details. They're not interested in the benefits that they're going to be able to bring to the house, because they're not like the builder or the architect or the owner. They don't have that level of commitment to the project. And in reality too, is like the electrician or the plumber or the framer, like they're framing houses all day long. They're framing regular code built houses, and they're going to come to your project. They're going to want to build it like they normally build it. And if we throw them strange details or things that are unfamiliar to them, the chances of them getting that right are going to be significantly decreased. So that's why we're trying to make them really, really standard and simple, to basically make it seem like that is a regular house. The other variable that we're looking at is using local cost-effective materials from the lumberyard. This kind of goes along with that. Number 2 is, if your subcontractors have never seen it before, there's a good chance they don't know how to install it properly. So trying to use normal materials that people are used to. And then the other variable is trying to make sure everybody's committed to the plan. And for us, in our case, if we're working with an owner, like 2 and an architect, the owner and us are usually committed already. But if you're in a project where only one person's committed, you at least need one person to start that process, and one person to have the knowledge and commitment. And then, as it says here, the level of success really depends on that shared knowledge and cooperation from the other 2 parties. So if you're working with a builder who doesn't know much about Passive House, as long as they're committed to learning about the process, they'll and excited to learn more about how to build a better house, then you're going to have a successful project. And so with that knowledge, this is what we're focusing on. These are the ingredients for our homes. Air tightness is number 1. We're using a lot more insulation. We're focusing on designing thermally broken envelopes. And with those first few, we're also taking into consideration vapor control and mitigation in our projects as well. And that comes down to choosing materials that aren't going to compromise our wall assemblies by creating issues with condensation in the walls. We are building other all electrical mechanicals and appliances. This is an all electric house. And the last one, which is really, really important, we really need to pay attention to the exterior details. So we're putting rain screens behind all of our claddings, and we're really paying attention to flashing details and air sealing. Something I've learned over the years is that if your house isn't airtight, then it will leak. Because a lot of that water leakage that we've seen in buildings is actually coming from suction, which is due to air pressure differentials on the house when it's windy and rainy. And you're creating negative pressure points on the house, especially around windows where you get little air leaks around windows, and water can actually get sucked right into the building. So that air tightness actually has a huge impact on flashing details. And then the icing on the cake for us is once we build this great envelope, we basically outfit it with air source heat pumps, a heat pump water heater, an energy recovery ventilator. We always use Zender in our homes. We're using Energy Star appliances and a heat pump dryer. So once you have that great envelope, you put these things into it, and these will all work in that envelope. They're made for each other. And then our process. So we've got all that information. So this is our process and how we put it together into this house. 90% of that work is our first process, which is design. And that's something I learned from working on our first passive house. That's always stuck with me is the traditional passive house process is that you're designing this whole project and then you're going through a pre-certification process. And in that first certified passive house I built, I realized before we started building that like 95% of everything we needed to do to certify the house was actually done on paper and in design. And the only variable that was left up to us was to follow the plans. And the only one that we were in control of that we could really mess up was the air barrier. Outside of that, all the energy modeling was done. The insulation was specified, the vapor profile of walls was specified. So we didn't have to think about too much besides just doing a good job following the plans. And so I really took that lesson to heart, and that's really why we've worked really hard as a company over the years to put more and more information and details into our plans just for that reason. And that's actually helped us to create more successful projects, and also kept our costs down, because the more detail, more information you have, the less chances there are for waste and changes in the field, which adds time and materials and money. The second part is just the build process, which, as it says, it should be easy, but yeah, there's too many humans involved, so we do have to pay attention there. So I've got some stuff for that to talk about that. So in our design process, we're really focusing on trying to create simple shapes and following the dimensions of the existing building products. So like, for example, this house right here, we're 20 feet wide right here going across, makes for really efficient use of sheet goods. We're selecting materials that are familiar to the trades and less difficult to install. HVAC, we're designing HVAC into the space. I'll show a slide about that. And we're also, which I think is really important, is we're engineering the HVAC. And again, this comes back to what I learned from passive houses. If we do a good envelope in the design process, we do our modeling, then we can make sure that the HVAC is right sized for the building. And especially so as we're actually moving from heat pumps, mini split heat pumps, to ducted air source heat pumps, which now means we have ductwork. And ductwork is really critical that we have the ductwork designed properly, just to make sure that the correct amount of air is going into spaces, to make sure we have the correct airflow so it's not a noisy system. And then also, which seems to happen way too often, is that the ductwork is not designed into the space. So you design a house and then the HVAC contractor shows up and someone's expecting them to just figure out how to get from A to B with their ductwork. And we're not allowing that to happen on our projects. So as we're moving more towards ductwork, it's a critical part of our phase is making sure we have the ductwork planned into the drawings. Another big variable about planning ahead is providing critical detail drawings. So we're not leaving crucial decisions to be made in the field. You'll see a couple of the drawings you'll see later. I'll show you some of the level of details that we're doing. And it's mostly in the areas where things that people aren't used to seeing, and sequencing things as well to make sure people understand if there's a tape detail, it has to be shown in the drawing so people can realize, oh, I got to get that piece of tape in there before we do that next level of framing. The other part of the design process for us is we're trying to do the problem solving in design. It's a lot easier on pen and paper than taking walls down and moving things around. Other couple of things we're thinking about too is like bathroom layouts and plumbing layouts in general. We're trying to minimize our pipe runs and like avoid using circulator pumps for our hot water. And then also choosing air barrier systems and shapes that don't rely on spray foam or a lot of additional work in order to achieve an air barrier. You can see like in this design right here, I mean, it's basically a simple box. So the air barrier, which we'll walk through that in a little bit, is just a simple square. So not a difficult shape to cover for an air barrier. Yeah, just an example of designing some of those design features in practice that you can see right here. Our building, this is the second floor of our Biscuit City Roadhouse. We're at 36 feet by, yes, 36 by 20. So really efficient use of sheet materials and all of our dimensional lumber. And specifically put this in, like, so we designed in a mechanical room. So like for example, I'm working with a consulting on a multifamily in Providence, and the architect doesn't even have a space for mechanicals drawn anywhere in the plan set. So they're going back to the drawing board, and I'm not sure if they're going to lose a unit or something to figure out where to put mechanicals. But in this small house here, we've actually created a little closet behind the closet. So you're in the bedroom, you open up your sliding doors, you've got a little coat closet, and then there's just a little door that swings in the back. We've got our heat pump water heater, and our Zender ERV is located back here. And this is a small room for the heat pump water heater. So what we did is we put a couple of grills to connect this room into the bathroom. Bathroom creates a lot of humidity from the shower being in there, and the heat pump water heater naturally dehumidifies. So those grills will actually open up the water heater to work more efficiently in this larger volume of air. And a little section on details, just to give you a sense of what we're looking at for what we're trying to achieve with our plan sets. So this right here is like the upper soffit. You can see we've got all of our trim laid out. And another interesting thing about I mentioned about using dimensional materials on this particular house, we designed the exterior trim. So you can see we've got these soffit boards here, and we got our fascia and a little drip edge piece. We designed all of that around the size of the material. So these are all pieces of 1x8 pine in the soffit. This entire house the trim was installed, with the exception of the windowsills, all the trim was installed without running it over a table saw. So it just came right off the pile and went right onto the house, just got cut to length. That was a big labor savings. And also we weren't buying a piece of wood, cutting off a section of it and throwing it away. You can see here, we've got our double stud wall. We're actually calling out our fire blocking. We've got our air barrier detail right here, where you can see there's a little bead of sealant right here to connect our sheathing on the wall to our OSB on the ceiling, with our seams taped. You can see our insulation. So basically we have all the parts in there. So when someone's framing the building or the insulator, they can see everything that's going in and how it affects them. Elevation drawings, just to give you a sense of the detail we're doing, is for example, it's kind of hard to see because of the shingles, but we actually have our shingle layout is all done in AutoCAD on the plan set. So we've got all those details in there as well. So we get to the build part. To break our build part up, we're focusing on 3 areas here. We've got our air barrier, our insulation, and our WRB. Those are really the main areas that we're looking at to achieve the shell that we're trying to build. So when I get into the air barrier, a couple of questions I always ask is where the air barrier goes, what needs to be sealed, and is it intentional? And it should be. It should be designed into the plans, and it should be detailed in the plans as well, so everybody knows where it is and why it's there. So in our plans, we start all the way down at the foundation. You can see we've got this is our vapor barrier under our slab, and it comes up, and we're on top of the foundation wall. We're covering this with a piece of Grace Vicor that's going to serve as our capillary break, and also creates a membrane to connect the interior air barrier which is the vapor barrier, to the exterior air barrier, which is going to be our sheathing. So that's all clearly detailed right here. We've got our tape from a Vicor to the vapor barrier, and then we were using a Sega Fentrum tape on the outside to connect our sheathing. to our to the Grace Vicor here, and also to our foundation wall. And there's another detail we've used. This is a different project where we actually caulk the sills as well, which is another option. So in here, you can see here's our Vicor that's carrying all the way through over the top of the foundation. And here's our sill plate. This is a slightly different design. So it's a 2x12 sill here for a different reason. But you can see we've got our caulk there's our caulk underneath the plates here. And we're also caulking where the plates meet together as well. Just another option for that air barrier. So once we get our sills taped, our next part of our air barriers are taping our sheathing, which, I mean, every building has sheathing on it. And I personally feel it is the easiest and most cost-effective way to create an air barrier in an airtight home. Because it's rare in construction where you can actually have one product serve 3 different purposes. So in this case, we got our sheathing. It's going to be our structural sheathing to hold our wall together, keep it from racking. It's also going to be the nail base for our siding in this case, which is one of the reasons why I'm really not a big fan of exterior insulation, is it really complicates installation of siding and flashing. In this case, the siding can get applied over a rain screen and nailed directly to the sheathing. So you've got a nail base for our siding, and then now we tape it, and now it can be our air barrier as well. So definitely a benefit there. And here's a picture from, this is a different project that we did, but I put this on here just to explain why we're using our sheathing as the air barrier. You can see in this photograph here, you've got our sill plate, and then we got our first mud sill. We've got our second mud sill, our floor sheathing, and then we got our walls framed. And see all these spaces in here. You can see the tongue and groove at the edge of the plywood. You've got all this space underneath the plates. We're shimming between the plates to make up for the unevenness of the concrete. And when you add all those spaces together, there's a lot of places for air to move. And we can see we've got our bead of caulk right here. And eventually this will have on the sheathing, onto that Vicor, and then onto the concrete, we'll have that Siga Fentrim tape. So that is basically going to eliminate the pathway between the caulk and the tape. That's going to eliminate any pathway for air to get up behind the sheathing and then come right through the sill area right here in these big gaps. So that's basically in a nutshell why I like exterior sheathing as the air barrier, because it's really covering all of this stuff that's happening underneath our with the framing. The thing you can see in this photograph too, it's kind of not very easy to see, but the top of the foundation here, you can see where it's been ground down a little bit. See, these are the ridges right here from standard concrete forms. First step for us before we put that Vicor down is we're hitting the top of our foundation with a grinder just to smooth out any ridges, take out any of the little humps. And while we're doing that, we'll just smooth the top inch or, well, probably 1 to 3 inches at the top of the foundation. And that creates a nice level surface for that tape. So otherwise the tape's going to be going over you can see all these little bumps of concrete, these little ridges from the forms, and that smooths all that out so the tape can be continuous all the way around. And also with that process too, if there's any mud, dirt, or anything else on there, it takes it all off. And then once we're done grinding, we blow everything off with an air hose, so it's a nice clean surface at that point. There's a couple more pictures of the sheathing. You can see we're using a pretty good sized bead of caulk. So as you're nailing it in, you do get a little bit of squeeze out. That's how you know that it's coming through. And actually, one of the reasons we did switch to the tape is part of having an air barrier is being able to inspect it. And we found with the caulks and the tapes, when we started subcontracting some of our work out, it was hard to tell if it was actually installed properly, if it was even there, because not everybody will put the correct amount on. So in this case, like I can see it here, but if we actually change that from a caulk detail to taping to cover that seam, as a contractor, I can go out, or my site supervisor can go out and actually see if that air barrier detail is being executed properly. And yeah, and here's the finished product right here. So we've got our zip sheathing in this case, we got our zip tape, and then here's our Siga tape to connect that foundation all the way through. What the other benefit to that Siga tape, which I really like, is you can see that bottom of the zip sheathing is now protected from any splashback. So if you have, let's say there was a patio here, like a stone patio, bluestone or something, when you get good driving rains, and that patio might be only 8 or 10 inches below, there's a lot of splashback that can happen there, and the concrete gets wet, and that you've got that exposed edge of the sheathing right there, and that I have seen that rot over time, especially if there's bushes growing up against the house. That basically will slow down the drying, or if it's on the north side of the house, same thing. And this tape will basically protect that edge of the sheathing from absorbing any of that moisture. Now, this next detail is connecting that wall air barrier, which is our sheathing right here. We're going to connect that through to the to our ceiling air barrier, which in this case, what we did is we took on top of our 2x6 walls, we actually built a 2x6 ceiling, and it was really simple detail where, because the building's only 20 feet wide, we're able to just frame a continuous ceiling with 20-foot 2x6s right across the whole building. That gave us a nice chase in here for running utilities, like we could run our Zender tubes through there. We've got a future house we've planned where we're able to run some ductwork through there. And then we've got our furring strips, wiring can still go in there easily. And so basically we ran our plywood all the way up, and then we put a bead of sealant here because of our plywood. We continued it up to create a back dam for our cellulose. But then that bead of sealant in here is connecting it through to an OSB on the top of that 2x6 joist. I've got pictures of that I'll show you in a second. And that ceiling air barrier becomes that OSB in the ceiling. We've also used Intello on the ceiling as well. And here's that same house, we've got a vaulted ceiling. So basically right here, we've got a piece of Intello that is connected to the top plate. That's going to flap over here and then connect through underneath the joist right here. So actually that Intello is not in the drawing there, but it should be, because came into the finished product. And there's one other thing I was going to point out here. Oh, actually, I'm not sure what it was, but we'll come up. It'll come to my mind. So here's that finished detail in place. So here's our sheathing coming up the wall. We ran a bead of tape right here first, because here's our plywood, our OSB air barrier in the ceiling. And we ran a bead of tape here just to create a bigger target for that caulk detail to connect the plywood sheathing here to the plywood sheathing in the roof. Oh, that was the other detail. See that deck up here of the OSB on top of the 2x6s, that actually created a platform for us to frame the roof. So if we were able to basically, we could frame this whole roof off of that's not a really tall attic in there, so we had like a 4-foot ladder up there. But basically give you a place to stand when you were working, which much more comfortable, much safer, and it really sped up the production on this particular job. And here it is from inside. You can see just simple 2x6 ceiling running all the way across. The size of this house too, and the shape, you can see we're able to frame this whole house without building any partitions. That's another part of another metric we try to insert into our designs to lower costs, and is to eliminate the structure. I find that a lot of larger houses, like we're building a house right now that's probably 2,500 square feet, so it's within the size limits that we're trying to work within. But the architect designed an extraordinarily complicated roof, and it's actually taking longer to frame the roof than it is to frame the walls in the house. That's how complicated that roof got. And like we've got point loads. There's probably 5 different point loads in the house. There's enough LVLs in that house to build probably 6 of these houses. I think the only LVLs in this entire house are just the roof headers. Sorry, the window headers. The only reason we're using window LVLs for window headers is just for the shrinkage. But otherwise there wouldn't even be any LVLs in this house. It would be all dimensional lumber. So yeah, we're able to build this whole ceiling all the way across without any partitions at all. And based on that airtight sheathing, these are the numbers that we're getting. These are 3 different projects that we've done over the years. These are the ones I have pictures of, but here we're continuously getting extraordinarily low numbers. The one on the left turned into like 0.12 air changes per hour. This one in the middle here was maybe 0.22. And this one right here is actually the house that the house that's presentation's about. They were at 49, which, gosh, that was probably around 0.17 or something like that. And those numbers are just from using that tape detail, a little bit of caulk at the sill, taping our sheathing, and then making sure that we've got that continuous connection from the wall sheathing to our roof air barrier, which in our case was the OSB in the ceiling. And then also connecting to the Intello and the sloped ceilings. So these were really, really, really great numbers. So next phase I want to get into is how we insulate our buildings. So in this particular project, because we're trying to create that thermal break at the foundation, this is an 8-inch concrete stem wall, which actually was an interesting thing that came up for us in design. Was I was looking at the code book, and I've been building for 25 years, and I don't think until 2 years ago I ever poured a foundation that was less than 10 inches wide. Doesn't matter what we were doing, it was always 10 inches wide. And I never realized that in the code you could actually you could form a foundation 6 inches wide if it's a frost wall. And so I talked to my code official and found out that, yeah, if you follow the code book, you can do that. And so all of our foundations now, which is new for our foundation guys, they question it all the time, but we're not doing 10 and 12-inch foundations anymore. We're doing 6-inch and 8-inch. So in this particular case, we have an 8-inch foundation wall. And also when the foundation wall gets narrower, your footing gets smaller. So when I added it up, it was, I don't know, between the footing and the walls, we basically reduced our concrete by about 30% or so. So we have an 8-inch wall here, and then for our thermal breakup at the top, just to create a little more R value right at the top of the foundation, between the exterior of the foundation and our slab, we have a 2-inch piece of type 9 EPS in here. This is another detail that we started doing that took a little bit of persuading with my foundation contractor, but eventually he did it, and now he does it for us all the time. And that's that we're actually just casting that EPS right in place in the wall. First few times we did this detail, I noticed that, well, first one we did, we actually built separate little forms and we set them in place. We basically built them out of plywood. They were perfect. They went in, we pulled them out, and we had this perfectly shaped shelf. And the forms were useless at that point because they were fit to a particular house, so they were covered with concrete, so we ended up throwing them all away. The next time the foundation contractor bought just regular pink foam from the lumberyard, they formed up their shelf, and when they were all done, they took the forms out, they pulled all the foam out, and then they threw it in the dumpster. At least the stuff that broke up and wasn't usable, they saved some of it, but it was maybe 50% waste. And then I asked him, and it took a couple of jobs before he finally did it. And I said, let's just take this type 9 EPS. We're going to nail it into the form. And you can see that pink line right there. That's the chalk line for top of concrete. So we basically they snapped their line and then they nailed this foam into the forms right into the line. And then that top of the foam becomes the screed point for the top of the concrete for the wall. And so now we're just casting it in place and we're just leaving it. which seems like such an obvious thing to do, but it was apparently it was pretty novel for at least where we are. It took a little convincing, but now that's a standard detail for us, and it's been working great. So that's where our installation starts. And normally I don't like to introduce other, like I don't like to ask the foundation guy to do installation work for us or anything analogous to that. But in this case, I mean, it's not too much of a curveball for them because that's how they form brick shelves traditionally. So we're just asking them to nail it up to the chalk line just to be a little more accurate with that. And even if they miss that, that's still fine, because we can always trim it and we can always add a little piece later. So that if it's not a perfectly detailed insulation joint, we can still work with it. This is the first house we did. We'd used Type 9 EPS in the slab, but in the second one that we're building right now, very similar home, we actually were able to use Glavel. And if anybody has a chance to at least try to price this into their project, I highly recommend looking into it. We actually found a net savings by using Glavel over EPS. I don't think that savings is as much anymore, but at the time we did this foundation, I think a 4x8 by 4-inch thick piece of EPS was around $96. So when we added up the square footage of that and compared it to the Glavel, and then we also accounted for the fact that we were going to be putting in 12 inches of crushed stone, and then we're paying carpenter rates to put in the insulation because it needed to go in really, really nicely. By the time we added up all those parts, we realized that, hey, the excavator can put this in. And by putting that in, we don't need to put in 12 inches of crushed stone. So we saved on a large quantity of crushed stone and basically replaced the stone with the Glavel. So the Glavel becomes our capillary break and becomes our insulation at the same time. So when we did all that accounting, it was a net savings of maybe $1,500 on this project. And the other nice variable there too is that the excavator is doing work that they're doing normally. So they're, instead of spreading stone around the foundation and leveling it and compacting it, they're just using Glavel instead. So it's not a huge leap for them. And as much as my carpentry crew knows that they do a good job with the foam, they're carpenters and they would rather be cutting and fitting wood than foam any day of the week. Which is an interesting anecdote because that's actually one of the reasons why we're moving away from exterior rigid insulation is when I look at all the projects that we've done that work on, we've never found it to be cost effective. And one of the things I keep seeing is when I do the estimates and look at the hourly rate that we're paying for a carpenter versus what an insulator is charging by an hourly rate, it doesn't make sense to pay carpenters to insulate. And all the projects we've ever been on, it's the carpenters doing the exterior insulation. And so they don't particularly enjoy doing it. And as a builder who's paying them, I'm paying a lot more money to provide an R value that I could achieve much more cost effectively by designing a system for the insulator to do the work that they traditionally do, which in our case would be dense packed cellulose, or if it's a regular wall, just batt insulation. So here's just the view from the inside of the house. This is a house where we use the EPS instead of the Glavel. And so you can see over here, there's our little 2-inch rip of foam. You can see the Vicor coming down over the top of the foam. And then we're covering it with our vapor barrier. And all of our pipes are coming through. They're all gasketed and taped to the air barrier for basically to be airtight and also vapor tight. We see a little airway blocked out where we had a shower drain. We have to get cut in after the tile goes in. And then on this particular house, we have a concrete floor going in. As you can see over here, it's that concrete floor is actually going to be our finished floor. So they pour it, and we're using what's called a burned finish. And that's basically it's a power troweled finish where they just run the trowel for an extra probably 2 hours or so. And it creates it's not a polished concrete floor, but it's a really, really smooth floor. Polishing gets really expensive. But it's basically an extraordinarily smooth concrete finish. And then we just put a sealer over it. And it's really the most cost-effective floor that we've ever been able to come up with. And for people that don't mind concrete as their finished floor, which I'm not one of those people, it's perfectly acceptable finish. And if it gets hard in areas, you put rugs over it. But myself, I'd rather have a wood floor. So here's our detail up at the top. This is a different house, but same concepts. You can see our air barrier across the ceiling, but this picture is just to show that's our OSB that we're bringing up to in this case, it's a truss. So it's basically going across the back of the truss to hold the insulation up. And the other project, the other detailed drawing I showed you, is just basically the back of the rafter tail. And then these are the vent chutes that we're putting in just to maintain that ventilation space for the once the insulation goes in. One of the reasons I wanted to show this detail is that this piece of OSB here is actually just scraps from the job site. As what we used to do is we used to run these AccuVents all the way down to the top plate. I didn't put a picture of that in here, but that thin plastic was never strong enough to hold up that 2 feet of cellulose and that tall of a piece, that tall of a amount of cellulose. So the installers would put in the vents and then they would actually hit them with closed cell spray foam, like just 2 inches or so, just to maintain the rigidity there. And we've been trying to eliminate the spray foam products from our projects. And by switching that detail over from the vent going all the way to the top plate and then spray foaming it, we're just tacking on the strip of plywood. So basically, after we cut out all of our windows from the first and second floor, we'll take all of those scraps and just rip them to whatever height that needs to be. And then it might mean we have to get a couple other strips as well, but we just nail them up because they don't need to be cut and fit perfectly. So all we're doing is holding up that cellulose there. So it's good, efficient use of materials. And then next part of our insulation, we're using double stud walls, and so really it just comes down to dense packed cellulose. So we're just netting the walls, blowing it in. That vaulted ceiling detail you can see here. We're using Intello in our ceilings in this case because we're want to manage the amount of moisture getting up into the roof. And then we've got our strapping to create the channel for our wires. And up in the attic here, a little hard to see, but yeah, we're probably around 24 inches or so there. And what's interesting, what you can actually see in this this yardstick here, how it's really hard to read the numbers on there. And what we found is over the last 2 years or so, the cellulose manufacturers have been putting a lot more cardboard in the cellulose. So you used to be able to look through the netting and just like you can see the little letters on all the cellulose everywhere. And now there's a lot of cardboard in there. And that cardboard actually is a much finer particle and it's got a little more static cling to it. So we're finding that the amount of dust that we're getting is like, gosh, 10 times as much as it used to be. So when you're going up into the attics and stuff, we can't even read the yardsticks anymore because it's just everything's just caked with dust. We're hoping we tried on the current project, and I think the next one we should be able to do is switch over to try that new wood fiber insulation from up in Maine. That should be an interesting experiment, which I think will be very successful. So the benefits of that insulation, this is the benefit during construction. So once we get the building envelope in, we start putting in monitors. So these are just little Accurate monitors we get from Amazon. We basically spread them around the house. So you can see we've got one in the first floor bedroom, one in the kitchen window, and one on the second floor. And so this is a house that does not have any HVAC installed, except for a couple of little electric heaters. In this case, this was probably around November in this house. And so with little electric heaters running for a couple hours a day, yeah, we're keeping the house at 70 plus degrees, and all by itself, we're around 50% humidity, which is really, really good for, October, November in Rhode Island. But what's most notable though is these are three completely different places within the envelope, and the consistency is really, really impressive. Um, and we're finding that throughout all of our projects. We've never seen big discrepancies at all. Even like last winter when we had that cold spell that came through where it went down to like -12, which is unheard of in Rhode Island. None of our customers had any issues whatsoever. Whereas like I knew people that had pipes freeze and had to leave their house, and not so for our projects. Nobody even noticed that weather was like that. One benefit of this too is during construction. So we find like we're not running propane heaters, we're not running kerosene heaters, and which both add a lot of moisture to the interior of the building during construction. We're able to maintain really, really comfortable temperatures which is good for our materials. It helps with drying when you're like with sheetrock and plaster. It helps with hardwood flooring. So if we're minimizing the amount of moisture that's in the building, then the subfloors are going to dry out quicker. And we're not going to have that excess moisture messing up hardwood floors. So it and also creates a great environment for people that are actually doing the work. So whoever's working in that house during the winter, they're really, really comfortable, which definitely helps with production. Last section I was going to get into was the WRB. And this is a really important point, is that there's no enforced code for flashing. There is language in the building code about flashing, but I have never in all my years, and maybe somebody here has experienced it, seen a building inspector call out a flashing detail in their inspections, which is really too bad, because as the building codes changed and as we're building tighter and tighter envelopes, there's so much less energy moving through our walls. And that's what used to keep all of our buildings dry before. So you go in older homes and you take them apart and you can see water damage, but there's minimal rot. And that's because there's a lot of heat going through the walls. The warm air gets heated up in the winter, blows right through the wall and dries everything out. And even in a code built house, you cover it with Typar, you've got your OSB sheathing, fiberglass bats, sheetrock, 3 layers of paint, and there's energy going through that wall, but not enough to dry it out. So you see a lot more rot in newer homes. Come to a high performance home with double stud walls, there's so little energy moving through that wall that if you do have a major leak of some kind due to a flashing failure, it's gonna be really bad, really fast. Like within a couple of years, you'll have mush back there. I think there was a story of an architect in Maine I know who did a mudroom addition, and the builder forgot to kick out flashing where that roof hit the wall. And he had 2 layers of polyiso and zip sheathing. He had 2 layers of polyiso on the building, zip sheathing, 2x6 wall with dense packed cellulose, and then sheetrock. And he didn't know there was a leak until the baseboard fell off the wall because the 15 gauge finish nail rusted out. That's when he knew he had a problem. So by the time they got in there, it was gone. Like there was nothing left. And that's what happens when you have a high performance wall and a major leak. That's the potential. So I'm not going to get into window details. That could be a whole nother session on its own. But you can see here's our zip sheathing, taped. And so we're prepping our window opening. That's our first step in our WRB, because we're starting we're continuing our air barrier from the sheathing into the window bucks. But then this blue tape becomes the connection point for our WRB where it meets the window. So we've got our window buck taped. This is our window trim units going in. And then you can see our cap flashings here. Those are our first line of defense for water. And then this tape right here, it's on the top, but it also runs down the side. And that's connecting this WRB, which in this case, this is the Proclima product called Fronta Quattro. It's basically the same as their as the Proclima Mento, but it's a little bit thicker, and it's all black, and it has UV inhibitors because it's designed to go behind an open rain screen. So in this part of the house, we have open. There's an open joint cladding there, so the sunlight's going to be coming through and water's going to be coming through. So that's why we're using that product here. But this tape here actually runs down the side as well, and that's connecting the Fronta Quattro to the window tape. So that's completely sealed. And we're using that black tape there because it's an open joint. You don't want to be able to see through that and then look at the blue tape. And so here's our siding going up. This is another project. So here we've got our Mento. In this case, we're using clapboards, and combined with, this is a shiplap pine. So we're basically running vertical furring strips to create our rain screen. And I get this question a lot. So we've got our the vertical furring strips are for the horizontal siding. The horizontal strips here are for the vertical siding. One of the things that we're trying to do is create airflow in here, and a lot of people worry about impeding airflow in between these spaces. So if I run horizontally, the air is not going to be able to flow through. It's a little hard to see, but what we're running continuous strips, but where the vertical strip meets the horizontal strip, we're leaving a good 3/4 to 1 inch airspace there. So air can move up and through, and if water does get back there, if there's enough, it'll flow to the sides and eventually get down to the bottom. And if it's back there, because you've got those spaces, the air can still flow through. So this space here is basically ready for siding. Here's a good example of that. So here's our vertical furring strip, and then you can see how it's spaced off of the window trim there. So now when the clapboard goes through, that little space right there between the clapboard and the window trim, if there's a leak, that's where the water is going to get through. So when it goes through that little space, then you've got this nice big open space in here, versus like if that furring strip was nailed up tight to the window buck, then any water that gets into that space between the clapboard and the window jamb is just going to hit this solid surface and basically just it'll just saturate that, versus having basically coming through to an open airspace where it can just drip right down. And that channel runs continuous all the way down to the bottom. So next part of that WRB, which is really critical, is detailing our penetrations. So this is basically the last section I want to go through with the presentation, is talking about the detailing these penetrations in our homes. I find that the air barrier and the flashing is really easy in the basic places. Like the air barrier in a house, when you're connecting from the sill and up, not that hard. Taping the sheathing, again, not that hard. And when you come over the top, if it's a simple detail, most anybody could, with a little bit of effort, have a really, really airtight box. But what I've learned over the years from blower door testing many projects is that as you make the house tighter, the places that are left leaking are concentrated now. So those pressures that exist in the house, when we're trying to manage our the moisture and energy flows through the building, in a leaky house, let's say in the wintertime, got warm air, it's got humidity in it, moisture in it, and that warm air is trying to leave the house. If it's a really leaky house, that warm air is flowing through the envelope in many places, and it's dispersed all over the place. And the house can sometimes handle it, sometimes it can't. As the house gets tighter, those pressures don't change. So if it's 20 degrees outside and 70 degrees inside, that's going to be a constant pressure. And as the house gets tighter, though that pressure is going to be concentrated in smaller and smaller spaces. A good example of this is when spray foam first hit our market, which was probably, gosh, 20 years ago, 18, 20 years ago, when the higher end builders and architects started specifying it, that within the first few winters, they were getting lots of calls of people with huge icicles coming out of their soffits. And the reason for that is because they were making the house much more airtight, but the spray foam was in the wall and it was in the roof. But that top plate connection, if you think back to that sill picture I showed you with all those spaces between the framing materials, those spaces exist in those double top plates. And the plywood where it attaches to that double top plate, there's a lot of space for air leakage there. It's at the top of the building. You understand the stack effect. There's a lot of pressure coming out through the top plate there. And all that warm air was going right into the soffits, hitting the cold soffits and then turning into water and then into ice. So that was a good example of that concentration point. And from that, I've learned that, so once you get this nice airtight envelope, you've got your zip sheathing, now we're going to start poking holes in it. And we really need to pay attention to them. So the first one here is basically outlets. So our go-to are these acrylic electrical boxes from the company in the Midwest called Airfoil. They used to sell them at EFI out of Massachusetts. I'm not sure if they are selling them anymore, but I really, really like these boxes. They are, basically, they won't rust out. I mean, traditionally in our area, builders use those little galvanized metal boxes. And gosh, I don't know how many of them, like 10 or 12 years later, you're modeling a house, or 20 years later, and the thing's just completely rotted out from water getting in there. So first of all, they're not going to rust and rot out on us. Second of all, they've got this nice big flange all the way around the outside. So we're able to basically just cut whatever size hole we want, screw it in, and then we're just taping it to the sheathing. And now you've got an airtight box. These are designed, I don't have a picture of the box separately, but this little piece of tape here, there's a rectangular space right here that you're supposed to fill with spray foam if you're using them on the interior of a building. So in this case, we're just taping it just to seal that off. That spray foam is basically to help seal that hole where the wire goes through the back of the box. But in this case, we're using this for the exterior flange and taping it to our sheathing. So now we have a completely airtight electrical box. You can see here it is in a finished situation. We've got a little block cut out for the outlet to get mounted to. So now any water that might get in there, it's sitting in a plastic box, which doesn't care if it gets wet, and it's not going to get sucked through any holes in that box and into the envelope. Another example, so this is our meter socket on a house. So we're bringing that wire from the outside. This is a roof-mounted electrical feed. So it comes down the side, comes into our box, and then now we get it from the box through the wall into the house. So in this case, we're using a piece of PVC with that's got the male end on it, and it's basically a little sleeve. We're putting a gasket on here. We use a lot of building gaskets from 475 Building Supply. Again, it's a Proclima product. And we're gasketing that sleeve, taping it to the wall, and then we're integrating that sleeve with our WRB here. So this is our air seal right here of the conduit to the gasket to the sheathing, which is our main air barrier. And then we're just covering that with in this case, this is an older project, so we're actually using tar paper. So now it's watertight shingle style, and it's also watertight and airtight with the tape in the gasket. And that threaded part just goes right into the back of the meter socket. Electrician runs their wires, and then from the inside or the outside, we just put a little spray foam in the pipe, basically to seal the space between the wires and the inside of the pipe. Another big one, faucets. So this goes back to the design part of things. We're trying to locate our exterior faucets in such a place that we're close to plumbing. So in this case right here, we're actually the same concept. We're using a little sleeve and a gasket taped to our WRB, but we're bringing that conduit in. In this case, this is the kitchen sink. So we designed this house and we specifically chose to put the faucet on the exterior wall behind the kitchen sink. So now that pipe's going to come right in to the sink base cabinet, and really quick connection for the plumber there. Main reason for this is, I'm sure a lot of people know, those frost-free hose valves. They're constantly breaking. They constantly need maintenance. And if somebody, which somebody happened to me on one of my projects, they left their hose attached to the frost-free faucet all winter long, which once you do that, it's not frost-free anymore. So that thing froze, and then it basically burst the casing. And then in the springtime, when they turn the faucet on, it basically just filled the whole wall. It was a double stud wall filled with cellulose. It filled the whole wall with water, which was we fixed it. It was a lot of work to fix it. It filled the wall and came out under the floor as well. And in this case here, if we had it in a sleeve like this, that water would have just filled into the base cabinet and gotten the floor wet, which would have been the same repair minus ripping the whole wall apart and taking all the cellulose out. So that's from that anecdote, that's the main reason we brought them in. But we'll bring, in this case, we're in a sink base in the kitchen. We'll bring them into a vanity sometimes. Sometimes we'll actually just bring it into the interior of a mechanical room, or we'll have them on the inside of a closet or something where they're not noticeable. So basically, once that pipes through the wall, comes into the back of the block, and the plumber can just attach a piece of a pipe to this frost-free valve and just push it right through. The pipe comes through the conduit in here, and then just like the electrical wire, we just put a little bead of foam in there to seal that up, and then they connect it to the inside plumbing. Last one's HVAC, and again, it's the same concept. Basically, these are going to be where the disconnects are. We've got 1, 2, 3, 3 compressors outside, and we're going to have 3 disconnects for those compressors. So we basically have a short piece of conduit with a threaded end, gasketed and taped to the wall, integrated with our WRB. There's our service outlet that's required by code, same outlet design. And we just started using these really nice flashing boots from Quick Flash for the HVAC. That the installers really like them because it makes it really easy to get that line set down and out of the building without the risk of kinking the line when they're doing it. And then once the siding goes up, these just poke through just enough so that they can take out the little knockout in the back of the box and put it right over that, thread it on there, run their wire through, and then just a little bead of caulk in there, or a little bead of spray foam, and that seals up that penetration. All right, I got through that a little faster than I thought, but yeah, hopefully there's some questions.
Thank you, Steve. That was a great presentation. You shared a lot of details, a lot of really good information, so I really appreciate it. We have some questions in the chat room, and folks,
oh, good.
Yeah, so I'll go through a few of them, but folks, feel free to add some more questions, and we'll get through this. You can also use the raise hand feature if you want to ask a question directly. But for now, just ask some questions to the chat room. But we'll start here, Steve. There are a few questions just kind of some details on the building envelope there. Yeah. So one question, you mentioned at the beginning you weren't using exterior insulation. So how are you hitting those R values that you mentioned? How are you kind of achieving the thermal barrier of passive house without using exterior insulation?
Oh, yeah, we're using a double stud wall.
So a double stud wall.
Yeah, a double stud wall, a dense packed cellulose. Basically we end up with an R42 or so. We're using a 2x6 exterior wall with advanced framing, and that's 24 on center, and then 2x4 interior wall, 16 on center. So we end up with about a 5.5 and 3.5, 9. Yeah, we end up with a 3-inch space in between the walls, but the studs don't line up either. So that creates our continuous insulation there. Okay. Yeah, we've done 2x8 walls with mineral wool and 2 inches of exterior rigid foam. We've done, what's the other insulation we used? We've used the wood fiberboard insulation. We've done exterior polyiso. And when we've looked at all those systems, the double stud wall is still the most affordable.
Hmm.
And it's not just the most affordable, it makes the sequencing's a lot easier for the trades. It makes it, we're building a normal house that way. Like there's when the average sub comes in, nobody knows that they're in a special house by using that system. Which, yeah, it makes everything a lot easier that way.
That's great. You mentioned liking to use the sheathing as the air barrier, and you showed a lot of Zip System photos. Zip System, of course, incorporates an air barrier into the product. There's a question of why do you choose that over just using, tape plywood sheathing?
Oh, yeah, we used zip sheathing for a while. We actually stopped using it for a little while because we were having issues with that OSB behind the green layer is not as high quality as the Advantech. So we were noticing a lot of swelling, and then like nails that were set flush all of a sudden would be back a strong 16th. In the end, I don't think it probably really matters at all. But then we switched over to CDX. And also because the CDX, we know what the perm rating is. There are still, when you get into the weeds of building science and really geeky builders, you get into like what's the real perm rating of zip sheathing, and CDX, like the tar paper that I showed in one of the from our older projects, is like a smart vapor retarder. It's more wetter it is, the more vapor open it is, and it can handle the wetting and drying of a mistake a lot more than the zip sheathing can. But we ended up going back to zip sheathing because the CDX we were getting was horrific. We were getting panels that were out of square. I didn't include it in here, but with my presentation I do on air sealing, I have slides showing like delamination and like whole sections of the outer layer of the plywood that are missing. So when you're taping that seam, the tape connects the sheathing, except in that spot where there's a football that's a void. And if you're not paying attention to that, you end up you lose some of the air tightness. But personally, I wish we could, like, we're using CDX. I wish we could get like, I guess I wish we could get a BC plywood, or at least get an AD or something to give us one flat fur face that's continuous. That would be nice. So that was the only reason. It was just it was a quality control issue from CDX. But personally, I like it better.
Okay. I think that really gets to the question there. You showed a lot of penetration details at the end, and there was a question about, are those in your plans, or maybe how detailed are the penetrations in your plans?
Not those aren't in there yet. And the reason for that, which there was actually a slide I realized I should have put in as I was doing the presentation, was on the build side, there's a list of things that we do as builders, as a contractor that's trying to maintain quality control. And one of the things I do is, when it comes to penetrations, we do those in-house. So if I'm subbing out the whole house, in my estimate, I'll put in, maybe 12 hours or 16 hours or 8 hours, depending on the size of the house, for someone, myself or one of my crew, to go over for a day. And they will do that detail. They'll cut the hole, put the box in. Like we actually, on the one of the elevation drawings I was saying, we had the siding layout. We actually have all those penetration locations are all specifically shown on the drawing off of the top of foundation. So anyone can go onto the plan site and come over 4 feet from the corner, come up 18 5/8 inches center of your box, cut it in. So right now we're doing those ourselves. But we are in the process of creating a catalog of drawings, not drawings, of sequence photos. Because I mean, it's really, I've never been able to take a drawing and give it to an electrician so they know exactly how to integrate a box into the WRB. But if you have a series of photographs that show each step, anybody can follow it at that point, unless they're blind. So eventually that will be, those will be an attachment to the specifications.
Yeah. I actually like that. I think the photos almost are getting to a higher level of detail.
Well, it's necessary. Yeah, we absolutely need that. Yeah.
That's great. You had someone was asking about spray foam. You had mentioned you're resistant to use it, or you're using it less than you used to. Is our if you could just kind of fill in the reasons for that?
Oh, it comes down to it's the carbon question. We're not actually doing carbon calculations on our projects yet,
Mhm.
but I'm very aware of the impact of the environmental. I'm aware of how the environmental qualities of the products we're using affect our homes. And like as a builder, if we're trying to reduce our carbon footprint of the buildings, then we need to carefully consider the materials we're choosing to put in there. So like that's why we're trying to reduce our cement
Yeah.
because at least in our area we can't get the concrete that has lower embodied carbon. Some places in the country maybe you can, but we can't where we are.
Yeah. I was
And
really impressed. You mentioned reducing the concrete by about 30% just by
oh
reducing the
yeah,
width of the wall. Yeah.
yep, yeah. Like we have a project coming up where we're using Glavel, and we've got a actually we the engineer let us do it. We've got a 6-inch stem wall. It's a frost
Okay.
wall with it's a single story ranch house. It's 6-inch stem wall. Like why not?
Yeah.
So yeah, that's the main reason for the spray foam is
Okay.
yeah, and it's actually
Yeah.
we realized too. We used to use spray foam and even in the rim joists. So we'd
Okay.
use cellulose everywhere, spray foam the rim joist because it was easier. But what we did on the last project is we had all the trades run all the wires and everything. A lot of the subcontractors, like electricians, they'll run all their wires on the perimeters.
Mhm.
But what we had them do is we have the space for it, just let's run it on the inside. I don't
Mhm.
want anything within 12 inches of the exterior wall. And then we were able to net and blow the rim joist easily because there was no wires and pipes in the way. So that allowed us and that also it was actually easier for the installation contractor because they don't want to mobilize a whole truck and drive 45 minutes and set up all that site protection and then spray for 15 minutes and then pack it all up and go home. So the cellulose person's there, all the materials are there. It's just, yeah, they just get to move forward what they're doing.
Great. There's some more questions in the chat that I'm going to come back to, but there is a hand raised. Hank, you can go ahead.
Steve, I want to say this is a fantastic presentation. You are clearly, a master builder in terms of your detailing and your knowledge of building science and the way you apply it to your buildings. And this presentation is going to be a fantastic addition to our library. So thank you very
Oh,
much.
you're welcome.
I also love the fact that you have given thought to the perm rating of zip sheathing. I feel like very few people have done that. And I'm thrilled that you have looked at that and gone to CDX. And I'm disappointed to hear you can't get good enough CDX to be confident
Yeah,
with it.
yeah.
That's hard to take. The do you have, when you avoid putting any insulation on the exterior of the sheathing,
Mhm.
do you have any concerns, whether it's ZIP or CDX, about moisture buildup, condensation on the back of the exterior sheathing, um, and the drying of that?
I do not. Um, in our assemblies, we're specifically using cellulose, which has a hygric buffering capacity. So when you actually, I'll go back. If you go even farther back than that, if you look at the interior space where people are living, we have the ventilation system, which is continuous. Um, so in the winter time, the ventilation system alone, unless they're mopping their floors every day with water or like filling the house with plants or have a lap pool in the basement, there's really no huge moisture load on the building. So that's the first thing we're looking at is where's the moisture coming from. The ventilation system can handle most of that. And if there is a case where they have a larger quantity of moisture building up, which we have monitors in the house that we check in every so often, and I leave them for the homeowners. They like seeing how that they can actually see humidity and temperature, and once they understand it, they start paying attention to it. And they're looking at the humidistat like they're looking at a thermostat now, which is pretty fascinating. And so once you get past that, the cellulose I think makes a huge difference. as far as its ability to store that moisture until you get to a drying time of the year. And then lastly, we're using Mento on the outside, which is extraordinarily vapor open. And then we've got our ventilated cladding. So it's a completely vapor open assembly that way. I mean, I think the weakest link in that assembly is the primer and 2 coats of paint on the inside of the wall, which is like a perm rating of 2 to 4, which that alone will eliminate a lot of that moisture transport into that wall assembly. I don't think people give enough credence to that. And then even with the zip sheathing, I think maybe it's a perm rating of 12, maybe. I don't know. No one's ever really gotten a real number from Huber. So between those two, like there's not a lot of room for it to get in or out anyways. The only way more moisture would get into that wall is if there was an air leak. So that's why we spend a lot of time on those penetrations. We flash for air tightness more than water tightness. And if you do that, you will get watertight as like a secondary benefit. So I think understanding how much moisture is actually getting in there. Like if we had a 2x6 wall with dense packed cellulose, yeah, or 2x6 wall with mineral wool, yeah, I might be a little nervous about that. So in an assembly like that, I'd probably put Intello on the interior wall and create like a secondary air barrier to manage the air-driven moisture.
Yeah.
But with a double stud wall, I'm not worried about it at all. I've been studying this stuff for about 15 or 16 years, and I have yet to see a single case study of a legitimate moisture issue with a double stud wall and cellulose that didn't have a reason that had nothing to do with building science in a well-constructed house. It was always due to settling or some massive moisture load or some other faulty construction detail.
Steve, a question just came up about this. You mentioned using maybe the wood fiber from Maine from Timber HP when it becomes available. Are you thinking of replacing the cellulose with blown in wood fiber, or are you looking at wood fiber boards for continuous insulation?
No, we would use the blown in version of it.
Okay.
Yeah, I don't like the cellulose we're getting right now. I really don't like it. It's extraordinarily dusty. It's yeah, it's something about it just gives me, it's not the same material.
Yeah, I'm curious to actually hear from more folks in Massachusetts if they're kind of experiencing that same thing with cellulose. We can have those discussions later, but that was
the cellulose we're getting now is actually more brown than newspaper color. So
all right, I'm going to go back to a couple questions here in the chat room. There was actually one. This is interesting one. What would be your recommendation for a customer wanting to add a wood stove in a passive house? Just in generally, how do you think that you could handle that, and what would that really change a lot of the other costs involved in the project?
Yeah, first of all, I say just don't do it. There's the Yankee Candle in the TV, and you could probably get a similar effect. But no, that comes down to the design. We'll actually take a space outside of the envelope, like a 3-season room or another room that's not part of that passive house envelope, and put the wood stove out there. You could manage everything with a wood stove in a passive house, except for the fact that you're going to cook yourself out of the house. Because there are passive house certified wood stoves and you're using little 6 and 9 inch logs. But the amount of BTUs they create, you're going to be too hot too fast. Like there's no way you're going to get that roaring fire hearth feel. You just can't do it responsibly inside an envelope like that.
Yeah. Another question, just trying to compare the slab on grade to basement foundations. Have you done any passive house is with basements, or are you doing all slab on grade?
Oh, we'll do basements as well.
Okay, and and I guess the question then is getting out, is it easier, or I guess what's easier, more cost effective, for the thermal boundary and the air boundary, slab on grade or doing a basement?
Oh, the slab on grade is more cost effective. Yeah, by far. It takes a little more coordination, a little more work up front, and during, like, just trying to get everything under the slab and get everything perfect. And yeah, framing it's a little tougher. Like you don't have any natural built-in storage space. Like where are you going to put all the plumbing stuff when it comes in before you're ready for it? Like there's no basement. But yeah, it's just more cost effective. And honestly, I think that's the only reason we've done slab on grade projects is because people we're trying to find ways to thread that needle today of the fact that it's just really, really expensive to build anything today. And people still need a place to live. They still want to have, enough space. And that's a variable that we put it out there and people are like, yeah, I don't really need a basement. A lot of these houses too, people are like, I don't have stuff anymore. Like I'm trying to eliminate stuff in my life. And so why do I need a basement? You know, but if you do want cheap square footage, that's a great place to put it. You know, but then we bring all those same building science details, we put them right into the basement. And the basements become extraordinarily comfortable places. And so, yeah, we can do it both ways.
Great. Thank
Really
you.
comes down to budget and design desires of the customer.
Great. Hank, your hand is up again. Is that right? Do you want to ask another question?
Yeah, one last question, which springs off what you just said, Steve. So we know that this house is fantastically much more energy efficient. The operating costs are much lower. But would you have a guesstimate as to the capital cost difference of this house versus it built to code?
Actually, what has a bigger impact is the material choices and and then who's building the house. That's what, like, people ask that question all the time. And yeah, you could find a less qualified, more cost-effective builder that just subs everything out and go to vinyl siding. There's a lot of things you could change in the house to lower the cost. But when I actually, I will say we have done cost analysis on larger projects where someone's really trying to squeeze money out of the project and like, well, let's just get rid of the double stud walls and the high performance details. And the last time we did it, it was like a $1.2 million house. And when we peeled all that stuff back and then added back in the stuff that you have to add back in, like increased HVAC, putting all the bath fans back in and ventilating the range and like all those other things you got to add back in there. And then add in the operating costs as well and the payback on that. It was around 4 or 5% maybe. Like they would have saved like $50,000 or something on $1 million house. And so when they saw that number, they're like, oh, okay, well, it doesn't make any sense. It wasn't like 20% or anything. But a lot of that comes down to also is the shape and design of the house. Like if that was a really complicated, let's say that this house was a really complicated cape with like 6 dormers and a turret on it, then yeah, making that high performance is much more expensive than trying to simplify the envelope. And so in that case, the spread might be 10-12% more. But with a simple envelope, it's really not that big. And I think what has a bigger impact on the cost of the building are the material specifications and the finish choices and who's building it. Like, are you hiring a bottom of the barrel builder that's $200 a square foot, or are you hiring someone that's qualified, who's not going to require extensive remodeling in 5 years when everything starts failing?
Well, we're at time here. This has been a great discussion. I know there's more questions. My apologies for not being able to get to all of them, but we are at the end of our scheduled time here, so I want to let folks go. Steve, really great presentation. Thank you again for putting this together.
Oh, you're welcome. No, it was a pleasure.